Hi everyone, we're Group 7 consisting of Congqin, Daeho, Mohammad, Yan, and myself, Kevin. We're going to be talking to you about the Hops file system and explaining how it works. A few topics that we're going to go over are the Hadoop file system, understanding HopsFS in detail, evaluating HopsFS and talking about the drawbacks of it, and finally a summary. So the Hops file system started its life as a research project to address certain issues that we find in HDFS. This will be covered in detail under the HDFS section. Hops builds on top of the TLS protocol, and it's a fully open source project. I will now hand it over to Yan to talk about HDFS.
The Hadoop Distributed File System (HDFS) is one of the most prominent file systems developed in their domain to support big data platforms. HDFS mainly consists of a metadata server called NameNode and a set of data servers called data nodes. The file system's metadata is stored in the metadata server's main memory, while the actual file's data is split into blocks that are replicated across the data nodes. HDFS metadata is stored on the heap of a single Java process called the active name node, which is also called ANN. The files are split into small blocks that are by default triple replicated across the data nodes. The metadata change log is replicated asynchronously to a standby name node, SVN, which also performs checkpointing functionalities. In HDFS, the Zookeeper coordination service enables both agreement on which machine is running the active name node, as well as coordinating failover from the active to the standby name node. HDFS metadata represents the structure of HDFS directories and files in a tree. It also includes the various attributes of directories and files, such as ownership, permissions, quotas, and replication factor. The name node execute file system namespace operations like opening, closing, and renaming files and directories, and also determines the mapping of blocks to data nodes. As for FS image, it contains the whole file system namespace, the mapping of blocks to files, and file system properties. The edit log, which is also called transaction log, is responsible for recording every change that appears in file system metadata. The data node stores HDFS data in files in its local file system and is responsible for serving read and write requests from the file system's clients. As stated above, we can conclude some limitations of HDFS. The first limitation with this architecture is that data structures are optimized to reduce their memory footprint, with the result that metadata is difficult to modify or export to external systems. And then HDFS does not address the limitations of the single active metadata server. Also, the number of files or directories stored on the file system is limited by the size of the metadata server's memory, up-limited by the maximum size of the JVM heap. Moreover, the metadata server runs as a Java process, where garbage collection process is inevitable. which would potentially disrupt the metadata server's operations, which will likely affect the performance of the metadata server. HDFS suffered from bottlenecks that limited its scalability, preventing it from supporting large clusters. That's why researchers developed HopsFS, a next-generation distributed hierarchy file system to mitigate the HDFS scalability bottlenecks.
This brings us to the next phase of file systems. HopsFS is a distribution of the Hadoop file system that's designed to tackle the limitations and shortcomings of HDFS. This is done primarily by replacing the single metadata architecture with a distributed metadata. The main subdivisions of HopsFS are the metadata storage layer, which consists of the network database called NDB, the metadata serving layer, and finally the block storage. So the metadata store is made up of multiple stateless metadata servers, which is responsible for decoupling metadata from the file system. This is based on the principle of separation of concerns. The metadata serving layer comprises of the data access layer, responsible for handling requests from clients and communicating with the block storage and metadata storage. Finally, the block storage is responsible for storing the actual data of the file system. When we introduced HDFS, we mentioned how it has a single metadata architecture, and that suffers from scalability bottlenecks, which limits the number of files and directories in a cluster. This is where HopsFS has the advantage because the design decouples storage of the file system's metadata from its access. We will now talk about each of the sections in detail, starting with the metadata storage layer. This is essentially a NewSQL database. The term NewSQL refers to databases that are a combination of the relational model with aspects of scalability and flexibility of data types. These databases focus on the features which are not present in NoSQL, while offering strong consistency. The NewSQL databases are a class of online transaction processing database that typically offer SQL APIs while maintaining the ACID properties. So a few advantages of NewSQL are it adds new implementations to the traditional relational database, and it brings together the advantages that SQL and NoSQL offer. The disadvantage, however, is the fact that it only offers partial features of the other two systems. Now, the metadata storage layer has a database which is a shared nothing in-memory distributed architecture. The network database called NDB partitions tables data horizontally across data nodes. We'll cover data nodes in detail in the next slide. A few features of the storage layer include high availability and throughput, and the real-time performance can be seen through features such as row-level locking, application-defined partitioning, which allows the user to override the default partition of the network database. Application-defined partitioning will be covered in detail later in this lecture. It also provides parallel transactions that can run across multiple partitions. Moving to the NDB itself, the network database. The network database forms the heart of HopsFS, and there are three parts to it. A typical NDB cluster consists of at least one management node, multiple data nodes, and one or more SQL servers, as seen in this figure. The management node is responsible for configuration and arbitration. Arbitration is the process by which a current node accesses and then releases control of data while passing it to another requesting process. So this can be seen in cases of network partitions. The MySQL servers are responsible for handling SQL queries submitted to the cluster. Apart from SQL, NDB also provides a native API to interact with the cluster. Finally, for fault tolerance, NDB replicates the table's data across the data nodes. These data nodes are organized into replication groups called node groups. So that's what we see here. Now we'll discuss the data nodes and node groups in detail. Each NDB data node within a node group contains a full replica of tables data for that specific node group. So that means if an NDB data node fails, the other nodes in the node group could take over. A cluster can survive as long as there is one alive data node in every node group. A data node is declared dead if it misses 4 heartbeat intervals in a row. These intervals are by default 20 seconds, but it can be changed based on the user's preference. For each partition in a node group, one NDB data node will be assigned as the primary, and the other nodes will be backups. For durability, the NDB data nodes record the in-memory data changes to redo and undo transaction logs on disk. The NDB data nodes asynchronously create checkpoints for the in-memory data to disk, and then they delete or truncate the logs to lower the size of the log files and shorten the data node recovery time. So this provides a global checkpointing protocol to write all ongoing transactions and their states to disk to survive cluster level and data node failures. So these are all the points we just discussed in regard to data nodes and fault tolerance. And you can go through this.
Hints are used to start the transaction on a transaction coordinator. In the partitioner scheme, inodes has a composite primary key consisting of parent inode's ID and the name of inode, with the parent's inode's ID acting as the partition key. In this slide, we introduce how a transaction was created. From the diagram, we can see when a metadata server in HopsFS receives a request, it will start a transaction on NDB. NDB first uses the hint supplied by the HopsFS partition key to locate the nodes that host the partitions for the transaction data. The nodes retained based on the hints are ordered with primary replicate first, followed by backup replicates. Then we determine which node of those nodes should be selected as transaction coordinator for that transaction based on the location domain ID. After selecting the best transaction coordinator, NDB runs the transaction on the selected transaction coordinator. Each NDB data node runs a group of threads categorized according to their functionalities, such as local data manager and transaction coordinator threads. The number of those threads is configurable and can be tuned to improve the performance of NDB. The local data manager threads are responsible for handling different tables partitions assigned to these data nodes. In contrast, transaction coordinator threads are responsible for handling all transactions, including cross-partition transactions in the cluster. NDB also provides distribution-aware transactions, enabling application developer to supply a transaction hint based on the partitioning scheme to enforce starting the transaction on a NDB data nodes that potentially has the required data for that transaction. Incorrect transaction hints will not cause any inconsistency, since the transaction coordinator will reroute the request to the appropriate local data manager that holds the required data. For concurrency control, NDB uses the strict two-phase locking protocol. The transaction protocol starts by acquiring all logs necessary and does not release those logs until the transaction commit point is reached. NDB always lock the primary replicate first, then the backup replicate to avoid deadlocks. NDB also implements a non-blocking distributed commit protocol that uses the two-phase commit protocol across raw, while using a linear two-phase commit protocol for each raw. A two-phase commit protocol is used to commit a transaction to write raws to two different partitions. First, the transaction coordinator sends the prepare message to the primary replicate, which propagates it to the backup replicates until it reaches the last backup replicate, which sends the prepare message to the transaction coordinator. Then the commit message is sent in the revised order to the last backup replicate. Once the commit message reaches the primary replicate, the logs are released on the primary replicate and a commit message is sent to the transaction coordinator. Once the transaction coordinator receives all the commit message from all the primary replicates for all raws, the transaction is committed and an acknowledgement is sent to the application. A transaction coordinator may fail while transactions are running. Therefore, NDB implements a transaction takeover protocol that elects another transaction coordinator, which reads the all ongoing transactions and proceed with the transactions as usual. An NDB cluster will survive as long as at least one data node in each node group is alive. NDB implements node value and heartbeat protocols to ensure agreement on which nodes have failed among surviving nodes in the cluster. To ensure leftness, NDB uses different timeouts such as transaction inactive timeout to abort the transaction if the client abandoned it, as well as transaction deadlock detection timeout to abort the transaction in case of nodes failure, high load, and deadlocks. Moreover, NDB implements a global checkout point protocol across the node group to allow system recovery in case of cluster failures. Primary key operation reads, writes, updates a single raw from a table in NDB using appropriate logs. NDB provides low latency and high throughput for this type of operation. It's the most efficient operation because it only infers to a single partition. It distributes the raws in a table based on the primary key if an application-defined partitioning is not used. If an application-defined partitioning is used, then the NDB uses the partition key instead. Ensure the operation runs on the NDB data nodes that holds the raws for the partition by leveraging the distribute aware transaction feature. We can ensure that the operation runs on the NDB data nodes that holds the raws for that partition. The second is batched primary key operation. It's an extension to the primary key operation which leverages the batching technique. Batching techniques are used in the traditional database to provide higher throughput at the cost of higher latency by making efficient use of network bandwidth. The third operation is partitioning prompt index scan. This operation is an index scan operation that is local to a single NDB partition. It needs to define an application-defined partitioning scheme for the tables. NDB will ensure that raws with the same partitioning key will always reside on the same partition. The fourth operation is index scan operation. It's a regular index scan operation that hits all partitions in NDB. It constant scale linearly with number of partitions compared to the partition pruned index scan operation that have a constant cost. The last operation is full table scan operation. This operation reads all rows in all the partitions in NDB without using any indexes.
To make sure that we share a common interpretation of metadata, let's see what metadata really is. Metadata is the data about the data. In this context, we'll include the reference to location of data blocks. Since we divide each file into some blocks, and the actual data block will be stored somewhere in the storage layer, we need to keep a reference to be able to access them. We have also to hold a reference to the location of the replicas. Block size, file permissions, directory quotas, and other related information about the actual data are called metadata. The metadata serving is that suppose a client wants to create a file in the file system. The location in which the client requests to create the file has to be specified. The permission, location of the replicas, and the quota of the parent directory has to be checked. As discussed earlier, in HDFS, the metadata is stored in the name nodes in memory. So a name node handles the client's request and the metadata storage simultaneously. In HopsFS, the metadata serving and storage has been decoupled in order to avoid a single point of failure as well as scaling out the metadata storage. Alright guys, having said all of that, so now let's see how HopsFS actually stores the file system metadata. As mentioned earlier, the metadata is stored fully normalized in NDB. Note that every node in the file system, including files and directories, are called inode. The file system metadata is represented as rows in tables on NDB. This figure shows the relational model used in HopsFS to store the tables. Each node, that is a file or a directory, is represented as a row in the inodes table. Similar to what we had in HDFS, a file consists of 0 or more data blocks, where the metadata for each block is represented as a row in the blocks table. The data blocks are replicated, where the metadata for each replica is represented as a row in a replicas table. Also, there are different tables to represent metadata for the different states of the blocks and replicas, such as under-replicated blocks, over-replicated blocks, and excess replicas. HopsFS has in total almost 90 tables to represent the file system's metadata and its supported features. So now, for instance, let's see how the metadata of this path is stored in the metadata storage layer. We earlier said that each inode, including files and directories, are represented as a row in the inodes table. Consequently, for each component in this path, which is a directory, we have a row in the inodes table. But we mentioned that we have multiple NDB servers in the storage layer. All of these NDB partitions have their own metadata tables, even though the relational model is the same in all shards. But how to distribute the information of these subsequent components of the path to access them efficiently? One way would be that to randomly store the metadata of these components in the NDB partitions. In this case, for example, if we want to use ls command to list the components under user directory, to retrieve the metadata, we must scan all the NDB shards to find the partition in which the metadata is stored. Next, we must scan the tables and find the relevant rows, and then put everything together and return the metadata. But remember that we said that the partitioning scheme is based on expected relative frequency of HDFS operations. List and read operations account for almost 95% of all operations. So it would be rational to shard the metadata in a way that the system could execute this kind of operations quickly and efficiently. There would be some file system operations which would be slowed down, but as discussed in the lectures, identifying the load of operations such as reads or writes is one of the most important aspects of designing the architecture of a distributed system. In this case, since list and read operations comprise the majority of the operations, the partitioning scheme will be based on that. In HopsFS partitioning scheme, all the tables except the inodes table are partitioned by the inode ID. That is, all the metadata related to an inode, whether it's a file or it's a directory, will reside on the same NDB partition. On the other hand, the inodes tables themselves are partitioned by their parent inode ID. This means that all the immediate children inodes will reside on the same NDB partition. To avoid making hotspots, which means a partition that will receive most of the requests, HopsFS implements a random partitioning scheme for the top-level directories. So this means that in our case, the metadata for these components will reside on one NDB partition. To elaborate more on that, suppose we have such a hierarchical file system. So for the top-level directories, we randomly assign them into the partitions, and the children of the top-level directories and all the related metadata, such as metadata for blocks and replicas, will consequently reside on the same partition. Now let's talk a little bit about the metadata serving layer. The metadata serving layer is responsible for handling file system requests from potentially thousands of HopsFS and HDFS clients. In HopsFS, metadata servers or namenodes are stateless servers that in parallel access and mutate the file system metadata stored on the metadata storage layer. The metadata servers use the data access layer to operate on the file system's metadata stored on NDB, which my fellow teammates touched upon that. You may have also noticed that we have a coordinator in the metadata serving layer called leader. The leader is responsible for housekeeping operations. For example, specifying the set of data nodes in which the data blocks will be stored and sending commands to the data nodes to delete invalidated or over-replicated blocks or replicate under-replicated blocks in the block storage layer. In summary, we have multiple servers operating on the metadata serving layer. The leader will operate as the coordinator. If a server fails to complete the transaction, the leader will notify the client to send the file system operation to another server. The leader election service runs every 2 seconds by default and ensures that there is only one active leader at a time, and this protocol is quorum based. Let's talk a little bit about how metadata serving layer takes care of file system operations requested by the clients. The file system's metadata operations are encapsulated in HopsFS Transactions that internally map to NDB Transactions, which were mentioned previously. HopsFS divides the file system metadata operations into two categories: inode operations and subtree operations. Inode operations operate on a single inode, whether it's a file or a directory, such as create, read, and delete a file, while subtree operations are operating on a subtree of the namespace, such as move, rename, and delete a directory, which could potentially have millions of children inodes. Every HopsFS Transactions runs in 4 phases: pre-transaction phase, lock acquire phase, transaction processing phase, and final phase to commit or roll back the transaction. We'll go through these phases by giving an example. Before going through the example, we must know that HopsFS uses the distribution-aware transaction feature provided by NDB to ensure the locality of HopsFS transactions. That is, a HopsFS transaction runs on the NDB node with all or most of the needed metadata for that transaction. This will require HopsFS to provide the partition key for the inodes table at the start of the transaction. In addition, HopsFS ensures that all file system metadata needed for a transaction are locked with a shared or exclusive lock before the transaction starts. Also, HopsFS uses the row-level locking primitive provided by NDB to serialize conflicting transactions. So now let's look at one example of an inode transaction. Suppose a client wants to create a directory into that path. The client sends the data to the metadata serving layer, which is responsible for handling the requests. Next, suppose the blue server is elected to serve the request. We check if the current client has the permission to perform this operation. We mentioned that the transaction is started on the database shard that holds all or most of the desired data. So in this step, we identify the NDB partition in which the majority of the metadata is stored. Then, batched operation reads all the file path components up to the penultimate path component without locking none of them. In the lock phase, metadata is locked and read from the database with the strongest lock that will be required for the duration of the transaction. Inode operations are path-based, and if they are not read-only operations, they only modify the last component of the path. If the lock has been already acquired, it means that there is an ongoing transaction taking place. Thus, the transaction will abort. Since the inodes are represented as rows in the tables, HopsFS uses the row-level locking to lock the inode row needed for the transaction in the table. Next, inode-related metadata such as block, replica, or any other needed metadata are read from the database in a predefined total order using partition-prune scans operations. It is important to know that all data that is read from the database is stored in a per-transaction cache as a snapshot that withholds the propagation of the updated cache records to the database until the end of transaction. The cache saves many round trips to the database as the metadata is often read and updated multiple times within the same transaction. Row-level locking of the metadata ensures the consistency of this cache. That is, no other transaction can update the metadata. Moreover, when the locks are released upon the completion of the transaction, the cache is then cleared. This ensures that if a name node fails during the transaction, the consistency of the metadata in the storage layer would not be affected. As a next step, we check if the destination has right permission and enough room to create a new directory. Then, the inode operation is performed by processing the metadata in the per-transaction cache. Updated and new metadata generated during the cache is sent to the database in batches in the final update phase. Then, the transaction is either committed or rolled back. If you remember, we had another type of file system operations which affects a large number of inodes. These kind of operations on large directories containing millions of inodes are too large to fit in a single transaction. Locking millions of rows in a transaction is not supported in existing online transaction processing systems. These operations include move, delete, change owner of a directory. For example, delete removes all the descendant inodes, and the set quota operation affects how all the descendant inodes consume disk space or how many files or directories they can create. The solution here in HopsFS is a protocol that implements subtree operations incrementally in batches of transactions. Instead of row-level database locks, our subtree operation protocol uses an application-level distributed locking mechanism to mark and isolate the subtrees. HopsFS serializes subtree operations by ensuring that all ongoing inode and subtree operations in a subtree complete before a newly requested subtree operation is executed. HopsFS implements this serialization property by enforcing the following invariants. 1. No new operations access the subtree until the operation completes. 2. The subtree is quiesced before the subtree operation starts. 3. No orphaned inodes or inconsistencies arise if failures occur. This means that each name node maintains a list of the active name nodes provided by the leader election service. If an operation encounters an inode with a subtree lock set and the name node ID of the subtree lock belongs to a dead name node, then the subtree lock is clear. However, it's important that when a name node that is executing a subtree operation fails, then it should not leave the subtree in an inconsistent state. The creation of per transaction cache mentioned earlier takes care of this. It is also worth mentioning that both inode and subtree locking mechanism are compatible with each other, respecting both of their corresponding locks. That is, a subtree flag cannot be set on a directory locked by an inode operation, and an inode operation voluntarily aborts the transaction when it encounters a directory with a subtree lock set. Next, my fellow teammate will talk about the block storage layer in HopsFS.
The block storage layer implementation of HopsFS implements the same architecture as its predecessor, which is HDFS. This layer holds the actual data associated with the metadata and stores files in a block store format. In block store, the files are split into 128 megabyte blocks, and each block is replicated usually by 3 different nodes in the block storage layer. Replicating each writing process multiple times ensures that a failure of a data node given the task of writing the file does not lead to the failure of the system. Replicating it 3 times is a good idea because in the case that we don't have access to the original and one of the replicas are corrupted, we can restore the information based on the other 2 replications. The number of replicas and the data node location in the network can be configured by the user, but by default, HopsFS users puts 1 replica in a node on the local rack, another replica in a node in a remote rack, and the last on another node on the remote rack we put the second replica in. This is because data nodes in HopsFS are not fully individually distributed, but rather in clusters or racks that are distributed, so this architecture also ensures against rack failure to an extent. The scalability bottleneck of HDFS of storing small files in the larger sized blocks is solved in current practices by not storing them with the larger files. This allows having different sized data blocks, which are key in optimizing storing space. So one of the solutions HopsFS offers in this hybrid architectures is using NVMe solid-state drives to store the small files on disk, while the blocks for larger files remain the same. Solid-state drives have much better response times with storing files in general, but cost expensive. HopsFS architecture supports optimizing usage and cost with a configurable threshold file size that redirects small files to be stored separately in SSDs. And this is a repeated theme in the HopsFS extended solutions to this scalability bottleneck. So some other ideas to note are HopsFS Cloud, which incorporates an algorithm that ensures that a data node in every cloud availability zone holds a replica of the file to write so that it can be accessed by those specific nodes in different physical locations. HopsFS S3 uses an object store in a combination with the original block storage layer. Using an object storage means that treating data as equal level objects or components within a data pool rather than fixed blocks in a sequence or hierarchy structure. Object storage has structural advantages in storing data with flexible file sizes and offer rich customization of metadata. In HopsFS S3, both block and object storage types are used to store data, and the block storage serves as cache servers for the object store for better performance.
Compared with HDFS, HopsFS achieves a large order of magnitude and higher throughput cluster. Cluster capacity has increased to at least 37 times that of HDFS. Experiments based on Spotify workload tracking show that the throughput supported by HopsFS is 16 to 37 times that of Apache HDFS. HopsFS also reduces the latency of many concurrent clients, and there is no downtime during failover. This picture shows that the HopsFS throughput is 60 times Spotify workload to 35 times, almost 20% write workload that of HDFS. As for this picture, the metadata capacity in HopsFS is at least 35 times that of Apache Hadoop, and it supports billions of files. As this figure, HDFS client latency is up to 10 times lower in HopsFS compared to HDFS for an increasing number of concurrent clients.
HopsFS provides a distributed solution to the scalability bottlenecks present in the HDFS architecture. However, HopsFS lacks support for an efficient and fast search mechanism as well as metadata replication functionality. Also, HopsFS uses a block reporting algorithm also deployed in HDFS that involves going over the entire directory list of the system periodically to ensure synchronization of data between nodes, which is largely deemed inefficient due to the fact that its overhead grows linearly with the number of data blocks. HopsFS also lacks support for scalable and high available deployments in cloud environments. However, a lot of these limitations come from a lack of research community around the architecture, which has not been in the trend in recent years as many cloud-native approaches to the HopsFS architecture have been developed. In summary, in HopsFS, the client requests and metadata are handled on the metadata serving layer, and storing is exclusively and separately done on the storage layer. Decoupling of data storage and serving layers adds scalability to the application and metadata. We discussed the architecture of the systems by its layers. We also discussed index node tables. Metadata is stored fully normalized in an inodes table where each file or directory is mapped to a single row. Inodes or index nodes can hold metadata and additional information describing the file or directory. We also covered how the system ensures availability to the metadata by using transactions and primitive locking by the database layer and the application-defined locking feature. Thank you for listening to our presentation.